Good morning, afternoon, or evening. This video is going to cover our unit rates guided notes. We'll talk about several different concepts in these guided notes, and I want to begin by talking about what a ratio is. A ratio is a comparison of two or more quantities by division. It can be written in a lot of different ways. One way is with a colon. We'll sometimes see that when we talk about the odds of a horse winning a horse race, or the odds of winning the lottery, or something similar to that. The word to can be used between the two values, or the phrase out of can be in between the two values. And we'll see each of these as we look at some of our examples. We can write a ratio of two things as a fraction in simplest form. Note that no decimal is allowed to remain in the numerator or denominator when it is in simplest form. And we'll see a few examples where we need to deal with that. And that's where it's going to be really important to see how to use your calculator. When writing a ratio using measurements, we want both quantities to have the same unit of measure. So we're going to come across some problems where we may need to convert some units of measure. So there are a couple of examples done for us here. The first example is 5 teachers to 125 students. Those are not units of measure, so we put 5 teachers over 125 students, and we simplify the fraction. We can do that as simply as putting the fraction in our calculator, and generally all you'll have to do is hit the equals key or equals sign in your calculator to simplify the fraction. It will do it automatically. There are some calculators that have a simplify button, so if you have one of those, you may have to hit the simplify button to simplify the fraction. In our second example, we have 3 inches to 5 feet. In this question, we do have measurements involved. So we need to recognize that in every foot there are 12 inches. So 5 feet is equivalent or equal to 60 inches as we have here. So we put the 3 inches on the top, the 5 feet on the bottom, and then you're going to notice that we're going to replace the 5 feet with 60 inches. So we have the same units of measure. Once we have the same units of measure, we're good to cross those units of measure out and just put 3 over 60 into our calculator, and that will simplify to 1/20. We'll also see some problems where we'll get improper fractions, and we will want to keep our improper fractions improper as we work through those problems. Now, in your guided notes, I did include both metric and customary system conversions, as well as time conversions that you may need to use throughout the school year, and especially in this lesson, or maybe later on in this unit. So you can always refer to these. They're on the back of the first page of the unit rates guided notes. Let's do a few examples, beginning with number 1. This one is already done for you. The directions ask us to write each ratio as a fraction in simplest form. For number 1, we have 34 points out of 98 points. So we put 34 points over 98 points. We can cross off those labels since we have the same unit of measure. If I put 34 over 98 in my calculator, it will simplify to 17 over 49. For question number 2, we have 87 oranges to 33 oranges. Now, we have the same unit of measure, so we'll put 87 oranges on the top, 33 oranges on the bottom. When we simplify that, our calculator probably isn't going to give us 29/11, which is an improper fraction. We will more than likely get a mixed number for this one. So in that case, we will get 2 7/11, which can then be converted into 29/11. We can do that using our calculators. We can also do it by hand as well. We'll talk about how to convert mixed numbers back into improper fractions as we get to some of those examples, but we do want to keep it as improper fractions. So we've seen a couple of different ways to represent ratios so far, using the words out of in number 1 and using the word to in question number 2. One of the most common ways we'll see ratios be written is with the colon, as you can see in number 3. So we have 72 cards to 30 cards. Put the 72 cards on top, 30 cards on the bottom, and we can cross off those common labels since we have the same label. Now, when I put 72 over 30 in my calculator, it actually gives me a mixed number automatically. Now, we can use our calculators change that into an improper fraction, or we can do it by hand, and we'll talk about that. But my calculator is going to spit out 2 2/5 as a solution. Now, to convert this into an improper fraction, I take the denominator 5 times the whole number 2, 5 times 2 is 10. I add the numerator, so 10 plus 2 is 12, and then I leave my denominator the same. So this is equivalent or equal to 12 fifths. Notice how we do stress usually putting labels on our solutions. We don't need labels on our ratios here. In question number 4, we're going to notice that we have some units of measurement. So we have 8 inches to 5 feet. We put 8 inches on the top, 5 feet on the bottom. Since every foot is 12 inches, to convert 5 feet into inches, we take 5 times 12 to get 60 inches. We will then replace the 5 feet. So I'm going to highlight this for us so we can see this. We're going to replace our 5 feet with 60 inches. Those are equivalent or equal, mean or represent the same thing. Once we have the same unit of measure, the 8 inches on the top and the 60 inches on the bottom, which used to be 5 feet, we can then simplify 8/60ths to 2/15. Let's take a look at another one. In question number 5, we have 1 ton to 45 pounds. We do use capital T to abbreviate tons, and every ton is 2,000 pounds. Now, a question I get from students is, how do we know which one to change? Should I change the tons or should I change the pounds? I generally recommend, I think it's easiest to change the measurement that is larger. Tons are definitely bigger than pounds, feet are definitely bigger than inches, and that's the one that we changed. Once we get down to number 6, miles will be bigger than yards, so we'll want to change or convert the miles. So what I did was I replaced our 1 ton, and again, I'll highlight some things here. I replaced 1 ton with 2,000 pounds. Now, I get 2,000 over 45. Now, unfortunately, my calculator is going to give me a mixed number that I will then need to convert into an improper fraction, and that will be 400 over 9. Let's take a look at question number 6, since this is one we have to do. So for this problem, we have 2 miles to 14 yards. Well, we can start by writing, whoops, sort of giving the answer away there. I didn't want to do that. We'll have 2 miles over 14 yards. Again, miles are bigger than yards. You've seen a yardstick probably before, or a meter stick. They're pretty similar. A mile is definitely going to be more. Every mile is 1,760 yards. Again, you don't have to memorize that. It's on the back of the first page. So in order to figure out how many yards are in 2 miles, just double the 1,760. That will be 3,520 yards. So at this point, let me not show you the answer. I am going to replace the 2 miles with 3,520 yards. You can see that we've replaced that, since those are equivalent or equal. Now that we have the same units of measure, though, we can cross those units of measure out. When I put 3,520 over 14 in my calculator, it gives me this mixed number, kind of a nasty mixed number, 251 3/7. So to convert that to an improper fraction, there is a button on my calculator, but we can talk about how to do this sort of by hand, but also using the calculator. We'll take our denominator of 7 times 251, get that solution, and add the 3 onto that, and put that number over 7, which is our denominator. Whoops, I'm going to try to move this guy out of the way. There we go. We end up with 1,760 over 7. Again, to repeat those steps, when we take 7 times 251, it's going to get us 1,757. Add 3 onto that to get 1,760 and keep the denominator the same. All right, let's roll right into our next problem. Let me move that up. Number 7 on the back of the first page. You can probably hear me flipping my paper as well. So we have 9 quarts to 5 gallons. So we will put, we'll kind of see this, 9 quarts over 5 gallons. Now, again, I recommended changing the measurement that's bigger. So think of quarts, think of gallons. Gallons are going to be bigger than quarts. Think of a gallon of milk. A quart is going to be much smaller. So I want to convert the gallons into quarts. Every gallon is going to be 4 quarts. Let's see if I can change the size of this. There we go. So 5 gallons is going to end up being 20 quarts. All I do is I take 4 times 5 to get 20 quarts. So I will replace the 5 gallons with quarts. Now I have the same units of measure. And again, just to stress, we replaced 5 gallons with 20 quarts. We have the same unit of measure. 9/20ths, if I try to simplify it in my calculator, it's just going to spit back out 9/20ths. So that's what we end up with for our solution. Now, numbers 8 and 9 involve decimals in a fraction. So let's talk about how to deal with that. In number 8, our units of measure are already the same. We have $1.20 to $3. So we put $1.20 on the top, $3 on the bottom. We crossed off our label, which is the dollar sign. But if I try to put 1.2 over 3 in my calculator and hit equals, it gives me an error message. There's a few calculators that will spit out the answer 2/5, but mine unfortunately will not. So here's the workaround for that. Take the decimal point in 1.2, move it to the right one place to end up with the number 12, but you have to do the same to the bottom as well to keep the fraction the same or equal or equivalent. So when I move the decimal point to the right one place in the number 3, I end up with 30. And if I put 12/30ths in my calculator, I'm going to get 2/5. So let's see how this works with number 9. We have 13.5 miles out of 30 miles. We'll put 13.5 miles on the top and 30 miles on the bottom. Again, it's really great if your calculator is going to let you put that in and give you the final solution. Mine will not, unfortunately. That means I've got to move the decimal point to the right one place. So in 13.5, I move it to the right of the 5, and it becomes 135. When I do that with the number 30, it means I'm going to have to add a 0 here. And so I end up with 135 out of 300. When I simplify that fraction, I put my calculator and hit equals, I get an answer, something we just saw recently, I get an answer of 9/20ths for that. All right, moving along to some really important usages of unit rates, which is the title of this lesson. So we talked about ratios, which we can represent as fractions in simplest form. That's a little less important. Let's talk a little bit about rates. So a rate is a ratio of two quantities that have different kinds of units. So for example, 400 miles to 14 gallons, $11 to 4 boxes. We have things specifically called unit rates, and these are things you see in real life quite often. So this is when a rate is simplified so that it has a denominator of 1. When you know you want to find a unit rate, think of the operation of division to find that unit rate. And the order in which we divide matters. Division is not something we can do in whatever order we want. So if you want to find miles per hour, which is a common unit rate that we see, you will divide the number of miles by the number of hours. If you want to find the cost per pound of an item, which again is another unit rate we see quite often whenever you go to the grocery store, you'll take the cost and divide it by the number of pounds. And that will get you the cost for 1 pound or cost per pound. The labels are also really important. You want to use the label of the first number followed by the word per or slash. We'll show you that. I'll actually represent unit rates in multiple different ways, and then the label of the second number. So there are a couple of examples that are done for us. The first one is that we purchase 6 pounds of shrimp for $51. Generally, we want to find the cost per pound. So we take the cost of $51 divided by 6 pounds, and our calculator is going to give us 8.5, so that means it is $8.50 per pound. What it means is that it's $8.50 for 1 pound of shrimp. Example 2. We travel 182 miles in 3.5 hours. We want to find the speed in miles per hour, so we take the number of miles of 182 and divide it by 3.5 or 3.5 hours. You can represent it either way. We end up getting a unit rate of 52 miles per hour, meaning we can travel 52 miles in 1 hour. Now, some of the questions are going to ask us to round to the nearest cent because we're finding the cost per pound or cost per ounce. When you are doing that, as a reminder, I know we already did a little prerequisite lesson on this, but rounding to the nearest cent is the same as rounding to the nearest hundredth. So we may come across some of those questions. All right, let's take a look at our first example. This one is done for us. Question number 10. It costs $58 for 5 tickets. Find the cost per ticket. Now, keywords here, we're trying to find the cost per ticket. We want to take the cost, which is $58, divided by the number of tickets, which is 5. My calculator spits out 11.6. Now again, labels are really important here. So we can represent that, since this is the cost per ticket, as $11.60 per ticket. All right, let's look at a really similar problem here. Number 11. 4 cans of soup cost $4.19. Find the cost per can. Round to the nearest cent. Since we are finding the cost per can, we want to take the cost, which is $4.19, divided by the number of cans, which is 4. We'll take $4.19 divided by 4 cans. I love putting my labels even in my work there. And even though I'm using my calculator, you notice I'm still showing this work. And my calculator is going to get me 1.0475. I did put cans of soup here. You could just put cans, is fine. Now we need to round to the nearest cent. So currently we have 4 cents, but that is immediately followed by a 7. We need to round the 4 cents up by 1 cent. We end up getting $1.05 per can. Right, you're going to look at number 12. It costs $274.90 for 6 people to attend a concert. Find the cost per person. Since we are finding the cost per person, we want to take, I want my highlighter back. We want to take the cost, which is $274.90, and we want to divide that by the number of people, which is 6 people. Now, we're going to get kind of a nasty decimal here, so our calculator is going to give us 45.16 with the 6 repeating. So you can see that bar notation for the repeating decimal. Your calculator might spit out a 7 at the end because it's rounding that last digit up, but there's not really a 7 there. It's just rounding that up to cut the decimal off at some point. So to the nearest cent, we currently have 81 cents, and since we're followed by a 6, that's going to round up to 82 cents. We can write this as $45.82 per person. You notice I use the slash for the word per instead of writing it out. That's another option. Sometimes you also have shortcuts like MPH for miles per hour, and that's going to come up in our next question. All right, let's take a look at number 13. It says, it took 12 hours to travel 565 miles. Find the speed in miles per hour. Round to the nearest tenth. So again, we're trying to find miles per hour. So we want to take the number of miles, which is 565, divide it by the number of hours, which is 12. When we do that, we end up getting, let me move that out of the way, 47.083 with the 3 repeating. So if we're rounding to the nearest tenth here, we currently have a 0 in the tenths place. Right next door, we have an 8. So that 0 is going to round up 1. We can write this as 47.1 miles per hour, or mph. Number 14, it costs $9 for 6 cans of beans. Find the cost per can. You're going to notice I'm highlighting what we're trying to find. That gives us a really good indication of how we divide and what order we divide. We want to take the cost of $9 and divide by 6 cans. When we do that, our calculator is going to give us 1.5. Now, the label we put on that is $1.50 per can. This time I did use the word per. Again, you can use the slash between the $1.50 and the word can as well. Remember, as I'm going through these, if you find the need to pause so you can copy things down, you are more than welcome to do so. I know that I go through them pretty quickly. That's because I already have the work typed up. You might have to pause as needed. So for number 15, a Frisbee travels 51 meters in 8 seconds. Find the speed in meters per second. So again, we're trying to find meters per second. We want to take the number of meters, which is 51 meters, divide that by 8 seconds. When we do that, we get 6.375. It doesn't ask us to round here, so we can write this whole thing out. So 6.375 meters per second. We don't typically use MPS for meters per second. It's not impossible to use it, but it's not a common abbreviation like MPH for miles per hour. All right, we have a couple more of these. Next one is number 16. So for number 16, it says it took a person 6 days to hike 108 miles. Determine how many miles the person hiked per day. We are trying to find the number of miles per day. We want to take our number of miles, which in this case is 108 miles, divide that by 6 days. Luckily, we end up with a really nice number here. We end up getting 18. We can represent our answer as 18 miles. We use MI to abbreviate miles, 18 miles per day. Taking a look at number 17, the last one of these straightforward unit rate questions. And again, unit rates are things we see in real life and can use to solve other problems. That's why they're really important for us. So 28 people spent $2,702 while on a trip. Find the amount spent per person. Since we are looking for the amount of money spent per person, take the cost or the amount of money, which is $2,700, divide it by the number of people, which is 28. Sorry, my silly gray box keeps moving back where I don't want it. When you divide those, you end up getting 96.5. We can represent that as $96.50 per person. Our next question, which apparently I did not cover up my work for this one, but let's take a look at it. In our next question, we're doing a real life kind of question, which is determining which is the best buy. So we have 3 different options. Again, you can see this work that's here. I can add the screen hide there. But we want to find which is the best buy. In order to do that, we want to find the shirt that has the lowest cost per shirt. So if we want to find the cost per shirt, we want to take the cost for each of those and divide it by the number of shirts. So for our first option, we're going to take $25.50 and divide it by 6 shirts. You can see my work there, and I got a cost of $4.25 per shirt. At the same time, I also had the 5 shirts for $21, the one all the way on the right. If I take $21 divided by 5 shirts, I get $4.20 per shirt. So that one is cheaper than our first option. It's going to cost less per shirt. And our final option is 4 shirts for $18. If we take $18 divided by 4 shirts, we get $4.50 per shirt. So the one with the highest cost is actually that one in the middle at the most expensive price per shirt. The one on the right is our cheapest or lowest cost per shirt. So we would say that, and I know we already saw this before I had covered it, but 5 shirts for $21 is the best buy since the cost per shirt is the lowest. All right, number 19, luckily I did cover this one up. Somehow I forgot that other one. We'll have to go back and fix that at some point. So number 19, at the grocery store, an 8-ounce jar of Nutella costs $3.25. Find the unit price of a jar of Nutella. So if we're trying to find the unit price, we're finding the cost per ounce, per pound, per fluid ounces, whatever weight measurement or size measurement that we're looking at. So in order to find the unit price, we want to take the cost of $3.25 and we want to divide that by 8 ounces. And it does say not to round, because we're actually going to use that answer for part B. We want the exact answer for that. So when we find the cost per ounce, we get around 41 cents per ounce, but the exact answer is 0.40625 per ounce, dollars per ounce. If we want to find the cost of a larger ounce jar of Nutella, 26.5 ounces to be exact, we can take that unit rate. We can use the unit rate and we can multiply it by the number of ounces we're going to purchase. So if we take the cost per ounce, which is 0.40625, using that exact answer, and multiply it by 26.5 ounces, we get 10.765625. Now, this one we do want to round, so we're talking about the cost, so we want to round to the nearest cent. We currently have 76 cents, followed by a 5, so that is going to round to 77 cents. That will be $10.77. All right, question number 20. Sanders family and the Gilman family are each taking road trips. The Sanders family travels at an average rate of 58 miles per hour, and the Gilman family travels at an average rate of 62 miles per hour. how far does each family travel after 5 hours? So, not a super difficult problem. We are actually given the unit rate here, and we want to use it to find the distance they travel after 5 hours. So, for the Sanders family, who's traveling at 58 miles per hour, we can multiply that 58 miles per hour times the number of hours they're traveling. And that's going to get us a total distance of 290 miles in that 5 hours. Similarly, for the Gilman family, they're traveling a little faster, so we can expect them to travel more miles in that same amount of time. So 62 miles per hour times 5 hours will travel a total distance of 310 miles in that same time frame. All right, now in our next set of questions, we're going to see something that's going to come back later on in the unit, which is identifying unit rates from graphs. So this is something we'll see later on in this unit or module, but it is a really good introduction for us. So in order to identify the unit rate from a graph, we want to look first at what the graph represents. And we're kind of seeing something similar to what we saw in the last question, but in number 21, we are looking at the number of miles that are traveled over a certain number of hours. So when we're thinking unit rate, we're thinking probably miles per hour or the number of miles in 1 hour. So if we're looking at the number of miles in 1 hour, we're trying to figure out 1 comma something, where does that touch our graph? So in 1 hour, how many miles are we traveling? Well, if we follow this up, let me use my green highlighter, 1 hour up until it touches this red line here, it's going to touch the line right here. Now, we have to follow that across to figure out how many miles are being traveled. We see that this line isn't labeled, but we can see that it looks like we're counting by 25s. So that means that that line would represent 50 miles. And in fact, I could label it here. Hopefully it'll let me do that. But I could label that with the number 50 right here. And that would mean that this family or this person is traveling 50 miles for every 1 hour. So our unit rate is 50 miles per hour. Basically, what you're looking for is 1 comma some number. You're looking at 1 on the x-axis, following it up until it hits your line, and then followed across to see where it hits the y-axis. So the unit rate is always going to be 1 comma some number. And again, we're going to see that later on this unit, but it is a really good introduction at this point. All right, for number 22, we're looking at Sarah's earnings over a certain number of hours. So if I look at this one right here and I follow it up, I'm noticing that this is going to hit the blue line kind of in the middle of the box or the middle here. And I'm not exactly sure where that is. If I follow it across, it looks like halfway between 20 and 25. But I don't really want to guess. So what I notice is that I do have a point up here pretty easy for me to identify. And that point is at 2 comma halfway between 40 and 50, which is 45. So that means, I'm going to go ahead and label that point for us. That means that in 2 hours, Sarah's going to earn $45. So we can find her earnings per hour because this is a straight line graph that passes through 0, 0, the origin. We can find that constant ratio or rate or unit rate. So what I did to find the unit rate here was I took $45 divided by 2 hours, and that ended up getting me $2.50 per hour. Now, if we go back to our graph, it looks like that was where it was going to hit anyway. So if we kind of follow this across, sorry, I didn't want necessarily the thick line there, but we knew that that was going to cost somewhere between $20 and $25 per hour. And we said it looked to be right around the middle. Halfway between 20 and 25 is actually $22.50 per hour. You can use other points on the graph to help you find the unit rate as needed. Our next question, we have our family road trip traveling a certain number of miles over a certain number of hours. So again, we're looking for that 1 comma some number ordered pair or point. So follow the 1 hour up, figure out how many miles that is. Looks like if we followed across, that's going to be 60 miles per hour. We could confirm this by checking this next point up. In 2 hours, we can see that this family traveled 120 miles. In fact, I'll label that ordered pair for us. we have 2 comma 120, and we take 120 miles divided by 2 hours, we also get 60 miles per hour. So it's not a bad idea to confirm. If we use any of these points on the graph, when we take our second number and divide it by our first number, our y divided by our x, we'll see that throughout this unit, we're always going to get 60 miles per hour. For example, in 4 hours, the family traveled 240 miles. 240 miles divided by 4 hours is also a unit rate of 60 miles per hour. In our last example with our graph, we have a certain amount of water that is consumed in liters over a certain number of days. We want to follow the 1 up when we do that. In 1 day, we are consuming 10 liters. So pretty simply, our unit rate is going to be 10 liters per day. Again, don't forget those labels. It really helps us to understand what that unit rate means or represents for us. Now, just some reminders for us as we head into the next set of questions. It's really important that you pay attention to the order in which you should divide when you're finding unit rates. So I want to remind you that if you're trying to find the cost per pound, make sure you take the cost divided by the number of pounds. If you're trying to find the miles per hour, divide the number of miles by the number of hours. And if you are trying to find the amount of rain per hour, for example, divide the number of inches of rain that fell by the number of hours. I'm reminding you of this just because I've seen lots of mistakes or errors with this in years past, so it's something important to kind of stress to us moving forward. So we are going to see some problems that involve fractions, and whenever we have fractions within a fraction, we call that a complex fraction. And when we divide, we're really just looking at fractions. So you may see some complex fractions moving forward, or you may hear that term. It just means a fraction within a fraction. Again, it's really important that you pay attention to the order in which you should divide. So let's look at number 25. Brian can run 2 2/3 miles in a half hour. Find his average speed in miles per hour. Again, we see here we're finding miles per hour. We want to take the number of miles, which is 2 2/3, divide that by the number of hours, which is 1/2, and we end up getting 5 1/3 miles per hour for his speed that he is running. Taking a look at number 26, a train traveled 495 miles in 6 3/5 hours. What is the speed of the train? So it doesn't say something per something, but we can imagine that's going to be miles per hour. We want to take the number of miles divided by the number of hours. That will be 495 miles divided by 6 3/5 hours. And we end up getting 75 miles per hour for the speed. Number 27. Brandon is making pillows for his couch. He bought 4.5 yards of fabric. His total cost was $36. What was the cost per yard? We can see we're trying to find the cost per yard. So let's take the cost, $36, divided by 4.5 yards. When we do that, we get a unit price or cost of $8 per yard. Number 28, over the last 5 3/4 hours, it snowed 10.5 inches. What was the average amount of snowfall per hour? We're finding the amount of snowfall, that's in inches per hour. That means we need to take 10.5 inches divided by 5 3/4 hours. Again, really important to pay attention to the order in which we divide. Sometimes students think, oh, it's always got to be the bigger number first. Not necessarily. In this case, it's inches per hour, so we take 10.5 divided by 5 3/4, and we get kind of a wonky fraction here, but we get 1 19/23 inches per hour. So about 2 inches per hour were falling at that time. All right. Moving ahead to our next question, I have to skip over some here. It says, an elephant charged 13.3 meters in 15 seconds. At this rate, how far would the elephant move if it could charge for 1 minute? So, not sure what it's charging at, but certainly a little scary when elephants are pretty large animals and wild animals, of course. But when we're looking at this, we're trying to find how far it could charge in 1 minute. We notice if we read really carefully, our time given is in seconds. So we have 15 seconds. We want to convert this to minutes. So 15 seconds out of a full minute is 15 seconds out of 60 seconds. That's a full minute. In order to figure out what fraction of a minute's 15 seconds is, we can set up the ratio 15 seconds to 60 seconds, and 15 over 60 simplifies or reduces to 1/4. That means 15 seconds is equivalent to 1/4 of a minute. The good news is on the Math 7 test, that hint is automatically given to you. The pre-algebra test, it isn't. Hopefully we can convert those. None of the measurements are super crazy, but basically we want to start with 15 seconds is the time period that's given out of 1 minute, which is 60 seconds, and that's going to be 1/4 of a minute. So to find the speed in meters per minute, we want to keep in mind that this 15 seconds is now equal to 1/4 of a minute. We can take 13.3 meters and divide that by 1/4 of a minute. When we do that, we end up getting 53.2 meters per minute. Let's take a look at another one of these, because I know they can be a little tricky. So in number 30, it says a speedboat travels 18 miles in 12 minutes. At this rate, how far will the boat go in 1 hour? Again, we're trying to find how far it's going to go in 1 hour, but our time is given in minutes. So 12 minutes out of 1 hour is equivalent to 60 minutes. So we can write this or represent this as 12 minutes out of 60 minutes, which is a full hour, gets us 1/5 of an hour. So 12 minutes is equal or equivalent to 1/5 of an hour. Again, that hint is going to be provided on the Math 7 test, not on the pre-algebra test. That's why we're practicing making that conversion. If we want to find the speed in miles per hour, because miles per minute isn't as useful, we're used to miles per hour, we'll take the 18-mile distance divided by 1/5 of an hour, which is that 12 minutes in time. 18 miles divided by 1/5 is going to end up getting us 90 miles per hour, which makes sense for a speedboat. All right, our next question, number 31. Missy rode the first 16 miles of a 20-mile bike race in 1 1/4 hours. What was her average speed in miles per hour? We know we are trying to find the number of miles per hour, and we know that she rode 16 miles in 1 1/4 hours. You might have noticed as you were reading through the problem, maybe even rereading it if needed, that we don't actually need the total distance of the bike race. We don't need that 20 miles. We know that Missy rode 16 miles in 1 1/4 hours. To find the unit rate miles per hour, we just need to not clone the box, but we need to take 16 miles and divide that by 1 1/4 hours. And that's going to end up getting us a speed that she is biking at 12 4/5 miles per hour. Again, sometimes we might give you this extra information you don't need. You can just ignore it. All right, last couple of questions. For number 32, it says Carpet Max advertises that they can install 1,260 square feet of carpet in 2 1/4 hours. Indicate whether each rate below is equivalent to this rate. So I would find the unit rate for the given value that we have. So I'm going to find the number of square feet per hour by taking 1,260 square feet divided by 2 1/4 hours. And that gets us 560 square feet. So let's look at each of these examples separately. In our first example, let's take the 820 square feet divided by 1 1/2 hours, and that gets us 546 2/3 square feet per hour. We can say that this is not equivalent. The box we're going to check is this one here. Our second row, 1,120 square feet divided by 2 hours, is going to get us 560 square feet per hour. So this one is equivalent to the original one that was given. And let's take a look at our last one. So 1,960 square feet divided by 3 1/2 hours gives us a unit rate of 560 square feet per hour. So this one is also going to be equivalent, so we can check this one. We just want to see, are these unit rates equivalent or equal? If they are, then we know that they will be equivalent rather than not equivalent. All right, our last question. So this problem, and I have a suggestion here that's not actually in your notes, but it says, explain why a student who runs 3/4 of a mile in 6 minutes is faster than a student, sorry, it says student, not student, who runs half mile in 5 minutes. Looks like a mistake I haven't fixed from last year. But as we're looking at these two students, I personally think it's easiest to figure out how many minutes it takes for each student to run 1 mile, like how many minutes for every mile rather than miles per minute, because in a minute you're not running a full mile. So I would take your number of minutes. In the case of the first student, that's 6 minutes to run 3/4 of a mile. So I took 6 minutes, divided by 3/4 mile. I was able to determine that it takes that first student 8 minutes to run a mile. For our second student, they're running a half mile in 5 minutes. So if I take 5 minutes divided by a half mile, I'm going to get 10 minutes per mile. It means that second student is going to take 10 minutes to run a mile, which means that that second student is going to take a little longer to run a mile. So my explanation here doesn't have to read exactly like mine, but I said that I found the unit rate. The first student will finish a mile in 8 minutes, but it will take the second student 10 minutes to finish a mile. So that means that first student is going to finish a mile faster than the second student. Now, I know I threw a lot of information your way, some simple unit rates, things that you see in real life for sure. We also threw in some slight word problems with unit rates. I can tell you that you really want to expect problems probably like 25 through 30 to show up on a quiz or a test. So make sure you go back and look at those as needed. We also threw in some graph problems. Those are things that are going to come up later in the unit, things that we'll continue to reinforce throughout the year as well. And we did throw in some higher level problems here towards the end just to reinforce this information. Unit rates is something we'll continue to review, so no need to panic if you still feel a little bit unsure, but I want to thank you for listening.